wind energy is really a big deal in Oklahoma. I mean, look at this chart. Okay, this is the wind farms in Oklahoma, and those black line is the high voltage line. Why do we need high voltage? To transmit power. If we send electricity at small voltage, same power. Like if I have like 50 megawatt coming from the Panhandle and going to Tulsa, if you send that over small voltage, the current will be so huge. Current so huge, there is that losses will be in the wire will be bigger, right? So you need to slow down the small current. So you do what? You have to increase the voltage, right? So for huge power transmission, you go over high voltage, and then only when you go to the neighborhood or the city, you have transformer to take you down, to step you down, right? So you can see that the black line, basically, we don't have enough of them, I think. We need more. But you can see how there is basically the windy place of the state, right? And this graph, look at this one. This is the retirement and the plant capacity in the US, utility scale. So they retired 14 gigawatts of mainly coal and natural gas power plants. 15 gigawatt. The Jinx power plant is 1 gigawatt, right? So that's like 14 power plants. Yeah, but I mean, China build one power plant every day, kind of, not every day, every month maybe or something. It's not a big deal too. But still, it's like 14 power plants shutting down. And here is what they are, the addition in solar and wind. Okay, so it is coming, right? But also, I don't want you to think of wind energy as just wind turbine. So what do you think is going on here in this picture? What is that? That's a sail. That's a rotating sail. So in experimental fluid, if you study rotating cylinder, if this thing rotates, you need the electric motor to run it. But if you just rotate a little bit and the wind is coming, so if the wind is coming and cylinder is standing in front of it, that generates drag. And it's a bad drag. That's a bad Viking ship, right? So a really good Viking ship will try to maximize the drag by I love Viking ships. So they will do this, right? And the wind will come behind them, and and the maximum they can go, right, is if this is U, I mean, let's make it V absolute. If that the wind speed, the maximum is U equal V, right? That's like a built-in wheel plate. You cannot run faster than the wind hitting you, right? But if you advance behind the Viking technology and you build yourself a sail that look like an airfoil, the wind could come like this, and because the boat is coming like moving like this, that would be, this is V absolute, and this is U. This become V relative. Why? Remember the equation, V relative plus U equal V absolute, right? So if you know the wind speed and you know the boat speed and you are trying to find V relative, you just connect them so that V relative plus U equal V. So what are you saying? I'm saying that boat running with crosswind will actually see the wind coming like this. And like in airfoil, a good airfoil will generate small drag, but huge lift component. So this lift force, it has a component that will move the boat forward, right? So with that technology, not only you can move against the wind with a crosswind, like Viking had to have the wind behind them, right? The wind has to come from, you know, this region so that they can move forward, right? But here, the wind actually, of course, the wind can come from behind you, but it can also come from in front of you. And you will still be able to move forward. Not only this, but in that old technology, U cannot be more than V absolute. But here, you can be moving faster than the wind that's blowing you, right? I'm not talking twice as much. I'm talking like you can be like 14 times moving faster than the wind. Why? So over here, why we couldn't run faster than the wind? Because if we run faster than the wind, we lose the push, right? We lose the guy that's hitting us. But this sail, no matter how fast he's moving, he cannot escape the crosswind. The crosswind is always pushing on him, right? So why I'm explaining sails? Because this is the two kind of turbine that we have. We have the Viking turbines that depend on drag, and they get pushed by, and they look like a sail or a cup or like something that trap the wind and the wind push on it. That guy can never run faster than the wind. And the regular three-plate turbine that you see everywhere, those are an airfoil. An airfoil sitting in a wind, and he can be running 14 times faster than the speed of the wind coming, and he still gets force from them. Okay? Make sense? All right. So of course, that airfoil also, you can do the same thing with a rotating cylinder. A rotating cylinder is just like an airfoil. As far as the wind, when you think about it, why does this lift get generated? What is so magic about going through an airfoil and when the wind come like this, why this big lift force get generated? Why? Pressure difference between the top and the bottom, right? The shape made it such that you make high pressure here, low pressure there, hence force will take you up, right? So that rotating cylinder, when you think about if the wind is coming like this, what will happen? Here you are moving against the wind, here you are moving with the wind, right? Near the wall. So moving with the wind, accelerate the speed, moving against the wind, slow down the speed, you are creating the same pressure difference, right? So people are thinking, of course, you know, like how there is like, we are trying to cap the emission from all industry. Cars started with cars, but the people in the Navy on all those ships, they are very nervous because they know they are second. They will come after them before they go after airplanes. And they burn the dirtiest fuel ever on diesel engines because it's cheap. They want to save energy, right? So they gonna be capped at one point. They will tell them, no, you cannot, or you're gonna burn that CO2, you pay this much. So there are all crazy ideas going on right now about like, well, let's make nuclear ships. Well, what if some bad people get this nuclear ship and you make a disaster with it, right? But also one idea is like, why don't we use electric, you know, sails like this? So when you use sailing, that is, you're not paying for the wind, but you have to put the sail and you let the wind do it, right? So those cylinders are a little bit more controllable, right? And less labor intensive, and and more robust. You know, the sail does not have to be replaced in case of a cylinder, right? So wind energy can really help beyond just let's rotate the turbine. We can also generate some thrust with it. Okay, very good. So here is the lucky people that have wind energy on land, right? At the end of the class, end of the lecture, I'm going to tell you that there is even, I don't see any, like this purple is here, right? So, but there is even higher velocity in that graph, right? It's say dark black, dark red, and blue. Where are this? Where would the velocity hit more than 10 meter per second? No, not here. Offshore. If we go out in the sea, we get even higher velocity. I can't hear. Say that again. Yeah, you're right. Yes, yes. Maybe on top of mountains and stuff, right? Yeah, the velocity will accelerate. But there's a lot, I'm telling you, there's a lot of red and blue outside. If we just put it in the so I mean some of the state, I forgot whether it's Iowa or I think it's Iowa, that they have enough energy from wind, cover all their energy expenses. In Oklahoma, I think I don't know now, we have like half or something coming from, so there is a lot of wind energy available for us, right? So you can see Oklahoma, right? Here's a better map that show the scale. All right. So here are the two turbine sides. So we said this is based on left force, and so there is no limit to how fast this RPM can be. And those are called horizontal axis wind turbine, because the axis of rotation is horizontal. Wind is coming like this, and we are horizontal. Of course, we have to rotate to face the wind. So all those turbines are basically moving with the wind. The American farm windmill, I remember the first time I saw one of those, I was undergrad, and I was fascinated by the tail mechanism that will push it in the right place. And what I really loved is that they had a spring on it, so that they tell you, well, if it's like solid, so basically what is the direction mechanism? It's just like a big sail coming here, big tail. And so if the wind is like moving in not right place, it will push it so that the tail is hiding, right? And it generates no force. But it's sitting on a spring so that you cannot push on it while it's rotating, because that will jack the whole thing up. So they put a spring so that the tail kind of push on the spring and then bring the later the turbine. It's like really, it was like one of the exciting moments of my career as an undergraduate student when I saw it and I understood how does it work. All right. So even the big guys, the three plates, they rotate, those huge one, this, yes, they do. But they rotate not with a tail, there is no tail. But they can tell, they have sensors on top that they can tell them which way the wind is blowing. And they have electric motor that rotate this huge thing to face the wind. But it does not rotate very quickly, so your eye will not watch it. You know, you have to sit, get your cup of coffee and look, wait for it until it moves. But they all move to face the wind. And there is a lot of room for innovation. If you like tinkering and coming up with new design, this is a very rich area where you can really improve. One of my friends, my office mate when I was a grad student, he had a company that came up with a patent just to retrofit existing wind turbine with small, devices that they put them on the wind plate to improve their efficiency. So you had already old wind turbine sitting there for 5 years, and you make new devices or like new things that you you go up on I don't know, helicopter, you just climb up and you basically put those guys in the right place. That improves the efficiency. So there is room for making new design. There is room to improve existing design. Okay. The horizontal axis wind turbine are drag based. Okay. So this is a air anemometer in any airport. Anytime you fly, you go to an airport, you see those cups, huh? And so no matter where the wind is coming from, those cups will rotate in what direction? Clockwise or counterclockwise? Clockwise, right? Because that drag on the open cup is more than the closed side, right? And this the same thing for this guy. But this guy is gonna rotate clockwise or counterclockwise? Yeah, right? So they will rotate, and sometimes you want to improve their chances by, you notice that, so I said no matter which way the wind is blowing, they will rotate in the same direction, right? That is the advantage. I think that's the only advantage of those turbines, is that they don't need orientation. They don't need a sophisticated mechanism to basically tell them wind is coming here, let's move, right? But the bad news is that there is part of the journey, like this part, where the plate is moving against the wind. That's right? So that's losses. So then again, room for innovation. Like this. Maybe you want to cover part of it. Maybe you can come up with a mechanism that slide it out of operation, or like make it, when it go to that place, become so thin or something, like morphine, you know? So that the plate changes. So there is a lot of patents on this to basically change the angle so that this guy will have an easy round while he's going against the wind, right? You can see it's one of the design here. So this guy moved with the wind to cover that part bad place. Yes, but they are all basically, at least here, they are all kind of drag based, right? Except this. So this Darius wind turbine, it's actually, we need to explain this a little bit. So this is 3 airfoil. Okay, and they are connected, I guess, with a shaft in the middle here, right? Let me show you. One of my students actually did his master on it. I have a cool picture. Here. So those 3 airfoil. So he in his master, he was trying to simulate those guys. So those 3 airfoil, huh, are just like a sail. And so they generate lift force like any airfoil. And that lift force, just like in the case of the boat, has a component that helps the plate rotate. So no matter whether the wind is coming from right or left, top or bottom, it will still rotate in that direction. So it generates left force, therefore it can really move faster than the wind, right? But just this configuration, like the other drag one, it has one part region. When it starts moving against the wind. So if the wind in this scenario, in this cartoon here, it's coming from left to right, right? Is it left to right? Yeah. From left to right. The wind is coming from left to right. When the plate is moving on the top, he's not really doing well, right? Because he's moving against the wind. But going down or going up, amazingly, he generates left force that will help him in that direction of rotation. Okay? Say that again. So this is circulation. This is basically a measure of how much circulation you have in the boundary. We are trying to figure out what speed will the wind end up basically damaging itself, because he end up swimming in his own wake. Like the bad separation reason, he was actually swimming in it. So, but anyway, I'm explaining that some of them has left force. This Darius form, it's actually generating left force, not drag, so it can move faster. So when we look at the efficiency of all those different design, don't be surprised if you see this guy swimming faster or like rotating faster than the wind speed, because he's left speed. But those guys, you'll find out that they cannot go any faster than their wind, right? Because they are drag based, right? And you can see here how this is a combination of drag and lift. I mean, you can couple them. Why would you do this? And you can couple them in such a way that one of them rotate the other one, but the other one can go and start faster. Then, like when you are paddling on like if you have a pike that has brakes in the paddle, not in the hand, right? You can brake with going backward, right? But the one with the hand brake, no, you cannot do this, because you can spin backward while the wheel will be like, no, I'm gonna move forward. So it's like two-way coupling or one-way coupling, basically. So they do this because this airfoil thing, in order for it to generate lift, that when I told you the boat travel like this, it required you to have V relative like this. If it wasn't for that U, if he was stagnant, if he was starting from the floor, from zero velocity, what is profile will look like? V absolute and V relative will be up, because U is zero. So the wind will come on the sail and do what to the sail? Will make the boat go forward. If the wind is all coming sideways, no V relative, it will just tip the thing back on the side, right? No, we need to turn the sail for it so that you get the right velocity. And as you pick up speed, and as your velocity profile is, instead of this, it start being this, and then start being this. You see what's the difference? This is V absolute, and zero boat velocity. This is V absolute and small boat velocity. This is V absolute and big boat velocity. So what is changing? What's changing is the direction of V relative. V relative, and here V relative is zero. So the sail here need to be ready for that wind. The sail here need to be ready for that wind. The sail here need to be ready for that wind. So when you are depending on the left, you need to adjust the plate to get the right V relative. V relative is what really drive you. Okay? So what if my plate is metal and he cannot rotate? Then at zero velocity, he will not really have a good left force generated. So we need something that is not sensitive to V relative, something that can start from scratch. That would be this guy, right?
There's two different sizes of that, right?
Say that again. No, the center is basically they are trying to make 4 plates like normal to each other. It's this is basically this. Yeah, they are basically doing like 2 cups like this.
Oh, I see.
Yeah, so one is normal to the other one. So they can, whether the wind is coming this way or normal to it, they will still be able to start. So the smaller guy rotate and start, and then once he start the bigger one now can leave him and start going faster because he's generating enough left to make him go spin faster and faster, and leave the smaller guy behind. Right? So I'm trying to say that tons of innovation, you know, you can make, and some of those guys, the drag one, when they rotate, they are just piece of art. I mean, I don't care how much electricity if they just like turn on one light lamp or one LED or like one iPhone charger in a bus stop, but they spin and they make this beautiful scene. They make them such that when they rotate, they end up like giving you this huge, it's a piece of art, basically, you know, with the right color, you can make things feel as if it's going forward or outward, right? Very good. So what is we wanna calculate for our homework today and the exam? What do we care about? We care about three quantity: CP, CF, and the levelized cost of energy, LCOE. Huh? Levelized cost of energy, that's basically the dollar per kilowatt hour. So in renewable energy, including the hydro that we studied last week, there is no cost for the fuel. Water is for free, wind is for free, solar is for free. The all cost is paid in the equipment up front. You pay $2 million to build this wind turbine, right? So what really it's important is not the efficiency of the turbine or the hydro plant. If the efficiency is 80% or 70%, we don't care. Huh? I mean, it's nice that we have, of course, as engineers, we try to make the efficiency go really higher, but they are not gonna buy that solar panel or wind turbine or the hydropower because the efficiency is amazingly 95%. Their decision is all based on this levelized cost of energy. How much is my kilowatt hour from this? If I build a natural gas power plant, I'm gonna get it with 50 cents. Are you gonna make me pay $1 for a kilowatt hour? Or are you gonna make me pay 12 cents or 5 cents or what, right? So how do we calculate the levelized cost of energy? That is the easiest calculation. Total cost divided by the total kilowatt hour in the life of this equipment, right? So if we know how much we make per year, how much kilowatt hour we generate per year, multiply by the lifespan of that thing, that's how much kilowatt hour you're gonna get. Yes? And what is the price? Right? That's it. That's levelized cost of energy. And of course the payback period is when I may get back my, you want me to put $2 million from my company money into this power plant or in this wind turbine or in this wind farm. When will I get my money back before I start even seeing profits? Right? So it's the total cost divided by the annual income. Right? It cost me $2 million and you're saying that I'm gonna get 200,000 every year income. So obviously I'm gonna make my money back in 10 years. The cost over the annual income, right? And graphically, it looked like this. Here is the year, right? And here is, so it's kind of, the cost is like total, huh? It's the initial, how much I lost day one. Day one, I lost, you know, how much is that? It's $3.35 million. Okay. So $35 million day one, and then in the first year, second year, why the loss is decreasing? Because I just made this in the first year, right? So my loss is now less. And so by the time I hit, say, year 11, the income times 11 years is equal to my initial, right? Of course, things can get a little bit more complicated if the turbine is, why the curve is sloping down. It's not straight line. What does it mean sloping down? That in the first year I made a lot of money. In the second year, not as much. In the last year, I'm not earning that much. Why? Curve is
With
meant the aging in general. The turbine at the beginning was making this much before it's not making that much energy. It also could be the maintenance cost is more. Every year, like as it get older, parts we cannot find parts, we have to make them, right? So, and this is, it get even more complicated because of, if it's not your money. So if that money is borrowed money, then you have not only to pay the money, but you have to pay interest. And depending on the interest rate, it may take you forever to recover from that investment, because the bank wants his money too. So the payback for the project is way longer. Okay, good. So are we clear how we can calculate? Because this is not in the book. So we wanna write this somewhere in this chapter 4, so that you can find this in the exam. How we can calculate the levelized cost of energy, the dollar per kilowatt hour. Total cost over total kilowatt hour in the lifespan of the project. Total cost, meaning that how much they pay upfront, how much I'm paying every year for maintenance, right? Total cost. How much money did I dump in? How much kilowatt hour did I get? That is the levelized cost of energy. That's why nuclear energy, by the way, when they came up with nuclear energy at the beginning, they was like, wow, energy will be so cheap, no one will have to pay his electric bill anymore. And it was like really like it's really like, you know, maybe 5 cents per kilowatt hour. But what they didn't count for is at the end of the nuclear power plant life, and it have to be commissioned, you need to clean it. You need to clean the site and seal the reactor. And guys, shut down this area. It's not going to be worked. That cost is going to be passed to the company. So that part of the levelized cost of energy. I mean, you need to do from what they call it, from gravel from birth to grave, basically, right? Analysis, the whole life cycle. All right, very good. So the other two things are CP and CF. The CP is our efficiency. Okay, it's really an efficiency, but people in wind energy say they tell you, no, don't call it efficiency. You call it power coefficient, but it's power output over power input. What's power output? The electric power you are getting from it. What's power input? We will see this in a minute. But like any kinetic energy, you know what's kinetic energy? What is the potential energy? In the homework this week, when we try to figure out how much energy is available for the wind, for the turbine, hydraulic turbine to extract, we said what? M dot, which was rho Q, multiplied by GH, right? Isn't that the input power that we calculated? B input, that's for potential energy, GH multiplied by M dot. What's unit of GH? Joule per kilogram. Okay, that's for wind, that's for hydro turbine. Now for wind, what is the kinetic energy in the air that we want to extract? What is it? And I want it in joule per kilogram too. I want it per unit mass. So potential was GH for hydro. For wind, it is just V. V is meter per second. I want joule per kilogram. I don't want m dot. I want it per kilogram. Let's keep the m dot outside here. What's inside? Just like m dot gh, kinetic energies per unit mass is gh is potential, kinetic. Huh? X one half, not m, v square. Okay, so without the m, it's joule per kilogram. Multiply by the m dot, it become joule per second. Right? Yes. So B input for wind coming to that turbine is m dot v square over 2. Why? Because v square over 2 is the joule per kilogram. You multiply by m dot, and that's the input power. In what unit? Watt. Right? Watt. Just like here. This was watt also. Make sense? So that's the input power. If we divide the output power, how much output power coming from the turbine over this, that would be the CP. Okay? And so it turned out, so I mean, we can basically say that CP is power output over power input, where this is power input. So it turned out that CP is capped. There is a efficiency maximum wind turbine can have. We saw in the hydro, 95 for Kaplan, right? But here, that limit, its limit is 59%. Cannot hit more than 59, and we'll see it in the graph, and we'll see the analysis too, right? And that's not, CB is not constant, it's function of the speed. We will see what is that function is. But ideally, when I run at the maximum efficiency available, just like the Kaplan, there is a curve. Why would you pick a turbine that's not peaking at its efficiency? Same thing here. If there's a curve for CB and you have a choice, run at the maximum. Of course, you can go off design because the wind is not blowing enough. You could get out of that sweet point. Yeah. Very good. But if you run at the right speed and the turbine is generating its rated power, you bought a 2 megawatt wind turbine, and that 2 megawatt wind turbine is generating 2 megawatt, that's heaven, right? 2 megawatt, you are driving the rated power all year long because the wind in that state or that site is amazingly cooperative and it's blowing at the right speed all the time, and you are generating the rated power all the time. What will happen then? You will generate the maximum possible energy, right? That's the maximum possible energy you can generate. Rated power, time, what's the 8760? What is that? 8760. That's the number of hours per year. 8,760. So if our turbine run at rated power all this time, that is the maximum generated, maximum possible energy you can generate. Unfortunately, you are not going to generate this. Why? Turbine does not run at rated power all the time. Why? The wind is not always listening. This is not does not run according to your dreams. So the turbine is available, but the wind is not available, or sometimes even the turbine is not available because maybe it needs time to orient because the wind just blew the other way. Maybe there is maintenance. There is a lot of reasons that make the actual kilowatt hour and the maximum possible are not the same. So when this happens, you get another kind of efficiency. I mean, it's kind of utilization efficiency. I had this thing and it's not working, right? Because the wind is not blowing. Thing is out of maintenance. The thing that is called the capacity factor. Okay. So unfortunately, that capacity factor is also not in the book. So I want you to write this in a good place in chapter 4. The capacity factor is the actual kilowatt hour generated divided by the maximum possible, which is rated time the 8760. What do you think the capacity factor for typical farms are? Wind farm. You think it's gonna be 10% or 90% or yeah, like 45, 50. Yeah, unfortunately, it's like 50, 45, right? I mean, sometimes it's even 35 because the wind is not always blowing there. I mean, and that's assuming the guy who picked it or the girl who picked the turbine did a good job because you could also have mismatch. So I was like looking at one site in a place I'm not gonna mention, and they have a capacity factor of 10%. I was like shocked because they put there is a mismatch between the site and that they picked a turbine that run at very, very high speed, and that speed is not available in that place. Right? So you can imagine big wind turbine with big plates will probably require stronger wind. We cannot put it in the atrium here and say, okay, give us our 1 megawatt. It's not gonna run. Yes?
So whenever you're doing the lifetime cost of energy, are you taking into account your capacity factor? And what kind of capacity factor would you use to calculate that?
We're gonna have fun calculate that capacity factor. There is two kind of problem. Capacity factor is given, that's the easy problem, or let's calculate the capacity factor. And we will do this after the break. So let's take a 10 minutes break and we will talk about the CB and CF for the rest of the lecture. So 10 minutes break and come back, guys. All right. So 45, I think we should continue. So what did we say about renewable energy in general? You pay upfront, you get annual income every year. You, after a certain number of years, you get your payback, 10 years, whatever, which is the total cost divided by how much you get every single year. How much do I get every single year? The kilowatt hour I'm selling time the price, right? And that's how basically you figure out what's the payback. So obviously we wanna maximize our income. We wanna, that's 2 megawatt turbine or whatever, we wanna get a lot of electricity out of it. So we want the CP to be really high and we want the CF to be really high. We want the turbine to perform as maximum as it's possible, and we want it to be running all the time at its rated power. So let's calculate those two guys and see how we can do anything to help. So what's the CB? Efficiency. What's efficiency? This is in the book. Output over input. What's the input? M dot input power is M dot V square. Half M dot V square. Half M dot V square. Okay, what's M dot? Always rho AV. Always rho AV. M dot is rho AV. Okay, rho air. How much is that? 1.2 kilogram per meter cube. And A and V need to be normal to each other, right? We said that that's how we calculate the flow rate. So what is the area? It's the rotor area, right? It's this disk. That's our area. So that area is I guess pi over 4d square, right? So pi over 4d square. But the rotor is not covering all that area. I mean, it's only the plates area is like smaller, but that's not your fault if you are the customer and I give them that area of the sky, that's their input area. We will see this over and over in solar, for example. If we give them all that projected area and they choose to make the sensor smaller or the heated area smaller, that's not our fault. Our budget start with the footprint. So we give you this much from the sky, you are responsible for this much input in energy, right? So area is the rotor area, right? And the V is V absolute. That's the wind speed coming in. Whatever that wind speed, that's basically the V. So that is the input power. So you can see you got V in the m dot and you got V square in the kinetic energy. So the input power, then it's what? It's half rho AV cube. V cube, that is a big power. V cube is a big deal. Huh? It's not V square anymore, V cube. So the difference between wind at 2 meters per second and wind at 3 meters per second is the difference between 8 and 27. Right? It's like 3 times bigger, just was going from 2 to 3. And going from 3 to 10, if the wind speed is 3 and the wind speed is 10, that's the difference between 27 and 1,000. Right? So that's why for wind energy, it's a big deal to go a little bit velocity higher. Cube. Cube such a power, strong power. Okay. So what is that CB? I mean, I to be great if it's 100%, right? But no, it's not. So the CB is on the y-axis over here. Okay. And this graph is not the one in your book. It's a little bit different. The one in the book is a little bit wrong, actually. It's wrong in switching this, and I think he's switching this with this. There's a problem in the graph over here, but at least this part is good. What is this part? It's the most famous one that we have right now, right? The three plate turbine. So y-axis you got CP. Okay, what's the x-axis? It's the tip speed ratio. Okay, omega r. What's omega r? It's the speed of the tip of the plate. So that U is omega, right? Omega time r, radius. So it's omega r divided by U infinity. What's U infinity? It's the velocity of the wind coming toward you. So if the plate is like sitting like this, U infinity will be coming, blowing on him, and he will rotate with a speed that is omega r. So can that tip velocity be faster than the wind? Yeah, 2 times, 4 times. Actually, our favorite, the 3 wind plate, ultimately it should run at 7 times the speed coming. If the wind is coming at 10, that tip should be moving at 30 meters per second. Can it do this? Yes, because it is a lift pace. It can rotate faster than the wind, and the wind will still hit it. It cannot run away from the wind. It's not a drag. Who is a drag? This guy. That's a bonus thing. The cups, kind of. You can see that it peak when it's moving at the same wind speed, 1. But you go and that's the tip. If the tip moving at 1, that means that the rest of the plate is, of course, moving less than 1. Right? So when it hits like even 1.5 or something, you can see that the CB is approaching 0 again. Because it can never run at the speed of the wind. You get 0 power from it. Okay. So if I'm choosing between each one of those guys has its own curve. This is the one that is rotating 3 plates. Remember they call it the egg beater too. Why the egg beater? Because the shape it look like those plates. They're like this, and they rotate like as if you are mixing the eggs for omelette in the morning. Okay. So if I am trying to pick between those guys, of course I'm gonna pick the 3 plates. And you can see the efficiency over here is very close to what? 0.49, right? So those 3 turbine plates, 3-plate turbine that you see them all over the place, their maximum efficiency is 0.49. Maximum. And no wind turbine will be created with more than this bits limit. And this is sitting at 0.59. So this graph explained to us why there is just 3 wind turbines, 3 plates everywhere, because that's how maximum they can get. Okay, and it also tells us that they, for maximum efficiency, maximum CP, you need to run at 7. What if you run a little bit slower than the wind, or a little bit faster than the wind, than the optimum speed, more or less more than 7? What will happen? Your CP will get lower. Okay, why would you do that? Well, maybe your RPM is fixed because of the generator and stuff, but the wind is moving faster than your target or lower than the target. Notice that this is a ratio, right? This is a ratio. So smaller turbine would run at different speed than big one. So big one, their omega R is so huge because their plate is 50, right? And they are running at same RPM for the generator. So those big one, to be at that sweet point, they need strong wind. But the smaller one will get that same ratio at a smaller wind velocity, right? Because the radius are small, right? And so what if I get a small one that's perfect for my farm, and it run at small speed, but then I have a really windy day one day? What will happen? I will end up going to that part and my CB will drop. Well, can't you accelerate? Maybe if it's running a pump or something that does not require velocity control, I can go up faster, and then I will go back to that sweet point by accelerating my wind turbine. So the torque, the resisting torque, remember chapter 2, the resisting torque control, there is a relation between that torque and the velocity, the RPM. If you tighten it, I can make that turbine go to 0 velocity, right? There is a maximum torque that if I do, I will break it. I will like break from braking, like I will let it stop, right? And if I put 0 torque, like I turn off the magnetic field generator or something, and my bearing is perfect, it will spin with 0 torque. It will go to maximum speed. So there is a little bit control on the speed sometimes, right? So that you can come to that sweet point and match the wind. We will see the control they do. They more than brakes. You'll see they have very sophisticated control because they wanna, surprisingly, they wanna sometimes want to be at that maximum point, but sometimes they don't want to be at that maximum point. That will be like what they on purpose slide off that maximum sweet point. Yes, they will. They wanna go down to smaller power. You have the ability to extract more power, and you don't. Yes, you will see now. What? Okay, but that curve what control the CP. Okay, so if we have a choice in the homework and in the exam, if you have a choice, and I say, you know, an American wind farm or like a Dutch wind farm or a Darius or 3-plate or 2-plate, if you have a choice and you are trying to figure out how much power you can extract, so I told you the wind, rho 1.2, and I'm not going to say 1.2, you will get 1.2 yourself. And the V is like 5 meters per second, and the diameter of the rotor is like 5 meters. It's American wind farm. Tell me what is the maximum power I can generate? I let your hand loose. You would say, well, I'm gonna American wind farm. You run here with efficiency or CP 0.3, right? And you better have that tip speed ratio. So from that you can calculate the RPM because you are aiming for that sweet point, right? So you come on this graph and say that is tip speed ratio 1. So your V is your WR, sorry, that your omega R, and you said that the radius is 2.5 meter. Here is your, and your CP is 0.3. Does this make sense? So if you have a choice, you will pick that best operating point, and you will get CB equal CB max for it. It's not gonna be 0.59. No one will get 0.59. You'll get that CB for that design, and you would say that lambda is lambda optimum from the graph. You will say, I wanna run at 7. It's my design, right? So this is lambda optimum, for example, 7. And what is that? It's omega R over the U infinity. So whatever wind speed you got, you multiply by 7 and you got yourself omega R. So I would ask you, what is power output from that wind site that you can extract? And what's the omega that you recommend we run at? And it's that point, the maximum point. If the other kind of problem is that I will give you an off design condition point. I would say, well, he's running at such that, you know, the tip speed ratio is like 10. Give me the bar output of that design. Okay, I cannot then assume it's CB max. I have to come here and say, well, if you run at 10, your CB unfortunately is 0.4. You come to this curve and read 0.4, and you would say, well, CP at that speed is 0.4, and here is your power output. What's power output? Power output is power input multiplied by CP. Yes? So if we can choose, we will choose the maximum CP for any design, and we get the corresponding optimum tip speed ratio. If we don't have a choice because there is already a generator connected running at certain speed with a certain gearbox, or there is a pump that need to run at that RPM for optimum pump load, the pump also needs its own RPM to run perfectly, right? Then we'll follow this curve. Make sense? Questions? So now, what is this magic limit? Why it's 0.59, right? And why no one can hit more than this? So that is shown in our book in the next 3 slides. This is all from the book. And so if you have a choice, like if someone asks you, try to find out what is maximum value for anything, efficiency of a turbine, profit of a company, any function. And he told you, we need to tell us what is the number of hours a worker should work in our factory so that we can get the maximum profit. Should we make him work 24 hours per day, or should we make him 0 hours per day? If we work 0 hours per day, we get 0 profit. If we make him work 24 hours per day, he will die in 3 days. So, I mean, there is an optimum number we need to. So how do we get that? How do we do it? If we have a variable that is the number of hours of workers per day, and we have a function, take the derivative of the function with respect to that variable. So there is energy extracted from this wind turbine, and there is a variable. Okay, and first, so this Spitz guy, he found out what is that variable. The variable here has to do with how much we slow down the velocity behind the turbine. So from our hydro last week, we got 100% efficiency from Belton wheel when the velocity after the turbine was 0. The water come at V1 because of the high dam that accelerated it in the nozzle, and then after the Belton wheel, 0 velocity, and the water dropped, they died at the end, and it just like fell by gravity. So it's the same question over here. what is the velocity after the wind turbine. If that velocity is 0, you would think I got my maximum energy, but you forgot that the power input is m dot v square over 2. So yes, v square was high before and v square is 0 after, but m dot could end up being 0 if you don't let the air go out, right? And so that's what he's trying to do in the next 3 pages. So the end result is he's basically getting that delta E, the energy change before and after. Okay? What's the energy? It's basically m dot kinetic energy, right? M dot v square. So here is the m dot kind of rho AV. You'll see it in a minute. Rho AV. And here is v square before and here is v square after. The velocity before and the velocity after. And so he called the velocity C. That's okay, right? And then the velocity after is C1 minus B. B is, how much is that reduction? If B is 1, then the velocity after is 0. He killed the velocity after the wind. And if B is 0, that wind turbine didn't do anything. The wind just went through, right? And so he's playing with that B. But it turned out that in order to slow down, you have to slow halfway in the middle first. So there is A and there is B. A is the reduction at the turbine plate, and B is the reduction after you leave the turbine. Why would you slow at the turbine plate? Because you just approach the wall. You have to slow before the wall so that you can go through the wall, those plates, and then you leave out, right? There is a relation between B and A. So they spend the first part trying to find out what is this relation between B and A, right? And it turned out that A is B over 2. So the geometry is such that you lose 50% at the turbine plate and then you lose the other after you. You lose 50% of your velocity at the turbine plate and you lose the other at the end. So if the velocity is 10 and you're going to slow it down to 2, so you are dropping 8 meters per second, that happened 4 and 4. You slow down by 4 meters per second at just before you cross and 4 after you leave. Okay, we'll see. It's all Bernoulli equation, continuity equation. There is nothing weird, but I'm just telling you the story from the end, and then we'll see the detail. Not that I'm asking you, I'm not going to ask you to drive this, but I really want you to understand how did he come up with it? Because in your senior design project, it's all about optimization. Most of the time, the design is all about optimizing something. And so I want you to have this idea, whether it's going to be differential equation or whether it is table that, you know, or like design space that you're going to see, well, here's my variable and here's my objective function, and how does it go down to a sweet spot or go up to a maximum spot? It's the same approach. So I want this to get into your head, that we try to optimize our system by looking at what is the goal, what is the knob that we have in our hand. And we switch the knob, calculate, switch, calculate, switch, calculate, and we look for this max. And that's what he did. But he got 2 knobs, B and A, right? And so in the first part of the derivation, he proved that actually A and B are not disconnected. They are connected. There is a relation between them. Just like this example, I use a worker in the factory, the worker and his food. You think, well, how many meals and how many hours he work per day? You think you have no, but maybe they are connected. The number of meals he eat is connected to the number of hours he work per day. There is not really 2 knobs. There is just 1 knob. He need to eat every, you know, whatever, 4 hours. Tummy start hurt, you need to give him food every 4 hours or something. Okay. So that knob, there's only 1 knob. And so he write the equation, dE, he write the equation in terms of this 1 knob. What is that knob? The A. How much reduction at the wind plate? How much reduction at the wind plate? Should we kill the wind at the wind plate by half, or so if we kill it by half, that means that the velocity at the exit would be 0. So B is the velocity reduction at the end, A is the velocity at the wind plate. So if you make A 0.5, that means that the velocity at the end is going to be 0. Yeah, so A is not going to be 0.5, right? So here is the energy, and here is the equation as function of A, and he differentiate dE by dA equal to 0. You do the differentiation, and the result, not surprisingly, A is not half, A is third. So if you make A third, you reduce the velocity by 1/3 and then another third, so it's 2/3. That is the maximum power. And so he substitute in the equation for the power output, and it turned out that the power extracted is 8/27, and the CP is the ratio. So that is this number, 0.5. Okay, that's the procedure. The maximum CP based on this is 0.59. And so now, how did he come up with that equation? You will see that he's basically looking at, here is the velocity before, here is the velocity after, right? So if we have like C over here, I'm going to have C1 minus A, and over here C1 minus B. And then he apply, what do you think is this? P plus half rho C square is B plus half rho C square multiplied by this ratio. This is Bernoulli equation between here and here. He's saying energy far away from the turbine to energy just before the turbine should be the same. Is that correct? Because no one is extracting or adding. As the wind slowed down because of the turbine plate, it didn't touch the plate yet. So this is like, I am slowing down because there is a turbine in front of me, but my energy is conserved. So as I slow down, my velocity go down, but my pressure go up. And once I leave the turbine, and then I go to the far away from it, right? What happened? Also, Bernoulli equation is applicable just before and farther downstream, right? Make sense? So you're looking at basically Bernoulli equation in the other extreme end, right? And then this is the momentum equation. This is simply the force before and after equal to the loss of kinetic energy, loss of momentum. If you remember, summation of the force is m dot v out minus m dot v in. Okay. So that's basically this. The pressure. So across the turbine, can we say that the energy before the turbine and the energy after turbine is the same? No, immediately before or immediately after. Can we say that the kinetic energy before and after is the same? No, the turbine extracts energy from them, right? But we can say that the pressure difference equal to the change of momentum. Change of momentum, linear momentum, m dot v. That's basically the Newton law, right? So that is this equation. So which turned out to be the force. This is the force. The change in the pressure is the force, right? So between those two equations, solving them together, that's what allowed him to basically find out that relation, that A is B over 2, yes. So he called the velocity as C. The input velocity is C in that derivation. He should call it V, I know, but we end up calling it C. Okay. So what will happen now is that he found the relation between A and B, right? And then he go after the energy. He basically look at, say, here, what is my kinetic energy? And what's my kinetic energy over here? And that difference, if there is a loss of kinetic energy between before and after, that is how much he extracts. And that is the function you want to maximize. It's like you want to maximize the profit to your store. You look at the budget, how much dollar does the guy come when he come in and how much money he leave with. The difference between the amount of money is what you got in your store. That's your profit, right? That's what he did. And so if we can figure out how much did the kinetic energy got lost between before and after, that's our energy extraction. Yes. So this is too far. Too far to the extent that the pressure is B infinity and B infinity. So the pressure, he is like far enough that the pressure is infinity. And just before and just after, P1 and B2. But very far away, it's P ambient and B ambient. Make sense? Right? So the derivation is very simple. I'm not going to ask you to do it, but I like you to be aware of the approach he did. And also, I want you to build that confidence that something so complicated you would think is solved by Bernoulli and continuity and momentum. That's it. So those three equations are very powerful. So no matter whatever you're doing in your senior design project, don't look down to the first law of thermodynamics. Don't look down to the continuity equation. You can do amazing stuff with those three conservation laws. All right? So now this Pitt's limit explain that solid line over here. But if you notice, all those guys, they are actually doing this. They are not even close. Right? So there is even more practical limit than Pitt's, which is this. Okay? And I want you to think why that is. I mean, this is like, especially here, is totally imaginary. I mean, we are not even going to get closer. Why? His analysis is mainly 1D. Flow calm. But what did we study in chapter 2? Those turbo machines. And I told you it's all about, what did we study in chapter 2? If we say it in 2 words. Chapter 2 was about, I can't hear. Yeah, but what is our turbo machines? What did I keep saying over and over and over? Angular momentum, the spinning, the whole thing was about let's rotate so that the rotor can rotate, so the rotor can get torque. It's all about angular momentum. So the wind leaving those wind turbine, they come straight. They need to spin them. How do they spin them? Because the wind come out spinning the other way. In his analysis, did he consider the components in the tangential direction? He saw that they come and they leave, but the way to do business, imagine if the way to do business in a certain country, you have to bribe people. Your company cannot sell generators in that company or turbine without bribing. That is, you have to take this into the budget. Everything, it's not just let's build this and sell it. There is an extra amount that has to go into it. So he didn't realize that the way to do business in that wind tunnel, as far as he's concerned, like let's slow down, energy is coming out, is that spinning. We need to leave out spinning. Right? You have to take this into account, which he didn't. And so he think that you can leave with that energy, but no, you need to spin, right? It's a big deal in the equation, right? Which will take even more from you, right? It's like, again, that store that we were trying to maximize our profit, but you don't realize that the way to do business is to give the people things in bags. You have to take the bags into account. Huh? So yes, you get their money, but you have to give them bags too. It's not just you get this exchange, dollar come here, goods go this way. Bags need to go in. Anger momentum need to be exchanged. All right? So if one of you can come up with a design that we don't have, they need to leave without twist, and they leave straight again, like, you know, counter rotating or something, huh? Then they could reduce the amount of energy that they have to lose at small speed, right? So it's really kind of cheating, you know, as far as I'm concerned, because this is my area. I'm not gonna say, well, you have bigger CP now because I'm gonna judge you on this. No, I'm judging you on like your input area, right? But you can see the effect that you are collecting from a bigger area, and you are basically, but you could see, well, something like this, you would say the turbine is so expensive, I rather have the turbine smaller and the collection is bigger. So that design is used in solar energy when the cell itself is very expensive, like very high quality. The cell is very expensive, so you put a collecting lens on top of it, and it take all that solar energy and put it to that tiny spot where that expensive high quality cell is. You bring the energy to it rather than building a bigger one, right? And they call that concentrating PV. So there is, like, you can spend hours looking at all those design, and every one of them is like really a fulfillment of your career as an engineer. You can improve them, you can come up with better design. If I have more time, you know, and more students, we will like, and 3D printer, we will just like print, test, right? Very good. So we understand now why there is 0.59. We understand also why he overshoot a little bit, but this is nice so that, you know, worst come to worst, if you don't have any curve, you don't know what turbine design they're gonna pick, you have this number in your head. This is just like the Carnot efficiency for wind energy. You tell yourself, people, the maximum efficiency is 59%. So whatever you think your wind is, we're only maximum possible in your dream. 59% of this is available for us. Okay? Someone say, well, we have this design and we are planning to use that wind in order to generate electricity. You tell them, what's your area? What's your velocity? 59 of this is available for you. Right? Very good. So now we are ready to do what? We are ready to calculate P out as CP multiplied by half rho A V V to power 3. Excellent. Right? That is, so now what is that V that we're going to use? We need to spend some time figuring out what is the V in that place. So in this graph, he's saying there is something called atmospheric boundary layer. When you take your experimental fluid course for 273, you will learn more about boundary layer. It's basically at the floor, the velocity is 0. No matter how high the velocity is on the top of the wind tunnel or in the duct. Why? Because if we zoom in here, and I teach a graduate course in the fall It's called microflow. So in microflow, we look at the fluid mechanics at really micro scale. And so at micro scale, if you zoom at the wall, what do you see? You will see that the wall is actually like this. No matter how you polish it, how clean it is, and how small is the molecules are here. So what I'm saying that the first layer of molecules, they are not on the wall. They are really in the wall. Whether that wall is an airplane wing or the street or the cities or a grass field, the first layer is stuck in the wall. Okay? Until you become a graduate student and take microflow and you start dealing with satellites and stuff and rarefied flow, then we can relax this. And I'll tell you, yes, we can slip on the wall for certain conditions. But as far as you're concerned, there is no slip boundary condition in fluid mechanics. No slip boundary condition, meaning that the boundary condition is such that the velocity here is 0 at the wall. Okay? Make sense? And then we go up with a curve. And that curve depends on how dense the place is. If there's a big roughness, like downtown Tulsa, building and churches and skyscraper towers and stuff, it take big distance, big height, so that you can go to that velocity. But if the thing is super smooth, like a very nice field, grass field, or like golf ball, yes, golf course or something, then it will be as if it's like this, as if the velocity is like one thing, right? Okay, so the roughness of the terrain decide that velocity profile. So why do we care about that velocity profile? Because most of the time, the measuring station, the tower with a cup anemometer that they have in Tulsa Airport is at a certain height, let's say 10 meters. And you're gonna buy a wind turbine that is 50 meters. And though that measurement say that the velocity is 7 meters per second, or like whatever, you wanna figure out what my turbine will see. That big turbine that we're gonna buy at 50 meters, I need to know what its velocity, because it's a big deal, because it's V cube. So I need to know, is it gonna be 7 like this, or if I'm upping over here, I will get 14 meters per second. What is that velocity profile? Yes. So that law, and that's why they build all those big tower. And you can see there are different cheap tower and expensive tower, depending on how high you are. Will follow that law. So that law is basically saying that U1 over U2. Unfortunately, this is also not in our book. And so this equation is very important. I want you to write it in your book, or make sure you have your lecture notes in the exam. So it's say U1 over U2 is Z1 over Z2 to power alpha. That alpha is the what? The wind shear coefficient. Alpha is the wind shear coefficient. So basically, that law will tell you if the velocity here is like 7, you know that the velocity higher you will be more, right? So if you did anything wrong, like flip this Z or something, you would know you were wrong. 10 meters per second, the velocity is 15. At 50, the velocity has to be higher than 15, cannot be lower. So now alpha is 0.2. I'm gonna give you alpha. You don't have to worry about it, but it's function of the nature of the terrain, smooth or rough. So different terrain will have different alpha. Okay. So if the velocity is just like one number, you said 7 meters per second here, tell me what's the velocity at the hub. That's piece of cake. One calculation and we are done. Yes. but the velocity does not come in one number. It come with a histogram. Huh? So they would collect the velocity at different pins, right? And they will tell you how does it look like. So what I'm saying is that let me plot it over here. So it will come like this. The data will be given to you in that form. V in meter per second. They will say all this table was done, say, at 10 meter height. At 10 meter height, the wind speed 1, 2, 3, 4, 5, 6, for example. And this is the hours per year. So the wind stayed here, you know, like 500 hours per year and 1,000 over here, 1,000 hours during the year and 1,000 over here. I mean, we need to make what? 8,760, right? And 4,000 over here. And so this is now how much? Make it 2,000. And here is 1,000. So now this is almost 8. It's 8 now, 1,000. And then this is the 260. Okay. So total hour sigma 8760. I'm going to give you a table like this. Okay. And then I want to know what is the velocity at, I want that table at 50 meters, because, or 100 meters, that's where my hub is going to be. So how do I do that? How do I find the equivalent table at 50 meters? And of course, alpha will be given. The shear factor for that place is 0.2. And the law is U1 over U2 is Z1 over Z2 to power alpha. Okay. And so here is the two height is 10 meter and 50 meter. And alpha is given. So can anyone help? What we are trying to do? We are trying to write this table at different height. Help. Meter per second, hours. Help me. What should I do? You have the table at 10 meter. We want the table at 50 meter because that's where. So this cup anemometer where they did the measurement is at 10 meter. Okay. So now I want to install a turbine at that place, at that airport where they did the measurement, but it's at 50 meter. Yeah. Yeah. 10 is where the data is, and 50 is where I want the new table. Your job is to get the table at 50 meters. What should we do? So this is the velocity and the velocity, meter per second, meter per second. And those are the two heights. So that law is explaining that velocity profile. This is U1 and say this is U2 and this is 10 and this is 50. 10 meter, 50 meters. So you are saying convert that velocity using that law, right? And turn this one into maybe, let's pick any number first, right? Let's make it 1.5 and 2.7 and 4 and 5.3, and this 5 becomes 6.7 and that 6 become 8.3. Okay. It's any number. I'm just putting them here. Huh? I mean, we can actually figure what's 10 over 50 to power 0.2. We can do that too. But let's just come up with any number. Okay, and then what? What's next? So Taylor is saying that when the velocity was 1 meter per second at 10 meter, huh? That's what the meaning of using that law is, that when the velocity was at that height, when the velocity was 1 meter per second, that law said then it should be 1.5 higher up. And when the velocity was 6 at that smaller height, it should be 8.3 at that height. Because I used 10 over 5 multiplied to power 0.2. Okay. All right, how can I fill this? The table. I want to finish the table. It will be the same number of hours. Excellent. So that's what's hard. That's when a lot of people get lost. So I wanted one of you to say it so that you can realize that it's not that hard. It's so when it was 1 meter per second down there for 500 hours, it's 1.5 up there for the same number of hours. That velocity profile below as one deal. Huh? This comes with one deal. When you come at 1 meter per second here, you are 1.5 there. If you are 7 or 6 meter per second down there for 260 hours per year, you will be that new number up there. Okay? And so the table will come like this, but sometimes it come a little bit more complicated in the form of wind rows. This is how the wind velocity is. Okay? So what is this chart is showing us, or this wind rows? The color show you the speed, meter per second, right? And the direction. Where is it coming from? That big thing, the wind is coming from the north all the time, or sometimes it's coming from the east. So it's the magnitude and the direction, right? And the length is how much time. So all those three are basically written in that wind rows, right? Of course, this can also be done in a 2D table, not 1D, 2D, where one direction have the velocity, the other direction have the direction. And the number are the hours. So what I'm saying is that the table can be like this. V, meter per second, 1, 2, 3, 4, 5, right? And then north, south, east, west, or if you want to get more sophisticated, you can break it into southeast, right? All the direction. And then in here, 20 hour, 30 hour, 40 hour, 50 hour, 60 hour. But when I add all those, the speed, the split by speed and split by direction, I will get what? 8760. Okay? So I love to give you that table in the homework because you will be handling like real data, right? Direction and velocity. Okay? And then the way we convert this, if this table was at 10 meters, and we want that table at 50 meters, what do we do? Which part we convert? Just the velocity. And the number of hours stay the same. The direction stay the same. We are only changing the label of the velocity. When it was 10 meters at that height, up there it will be a little bit bigger. Make sense? Very good. So so this is the 1D table, no direction. So you can see here is the the bends, or like the places where the counter, where they are counting the speed, and that is the speed: 0 velocity, 0 to 1, 1 to 2. So people sometimes get confused, like, so the velocity stay between 1 and 2 for 496 hours per year. Again, the total, if I add all the total over here, I should get 8760. So they get confused, like, so what is the velocity over here? Yeah, so I mean, I need that velocity for something. I need to, if you're gonna turn this table, see, he said use alpha 0.2, right? And you wanna turn the table to certain places, certain height, turbine height. So what velocity I should use for that bend? No? Yeah, I would use 1.5. I would use 1.5, right? I mean, if you're gonna move 1 and 2 and say, well, here is the new velocity at that new place in that range, that's okay too. But just pick the middle and say, well, the velocity in that place was 1.5. So now at 50, it will be that new velocity. Done. Make sense? Okay. So the number of hours per year, I mean, if we divide over the total, which is 8760, you can also get a percentage, right? And so if we plot this, instead of like those weird number of like 600 hour here and 700 hour here and 1000, 1200 hour here, we get, we plot the frequency. We get 0.1, we get 0.2, we get 0.3. That is sound more scientific, kind of. It's like the percentage of time. So that would become, if you plot this, it will be the frequency distribution function, BDF, the probability distribution function, right? The probability distribution function. It's basically, you are saying that this is the percentage of time the wind will stay in that nice velocity spot, right? So there is a danger here that when they collect that table for the whole year and they write the number of hours per year, and you plot that distribution, and that distribution is like, say, something like this, and you'd say, well, I get the average velocity, or most of the time the velocity is in a really good range. I can run the wind turbine and I will get enough power. The danger is that that number of hours per year, maybe they all happen in the summer months, and the winter was dead. So basically what I'm saying is that this nice velocity was all the summer months, and this basically is winter, spring, and this is the fall or something. Ouch. So that means that turbine will not be running for like most of the year. Yes, the average is okay, and you will get your power during the summer months. We will do the calculation. You get enough energy, but the seasonal change is a big deal too in wind, right? And let's not even go for the daily variation. I mean, what if, like, no, this happened every single year, every single day of the year? That's great. I mean, the average is pretty good every single. It's not like just summer wind and winter no wind. No, it's all year long. That's the average. It's pretty good, but it happened only at night, not in the morning. It's very windy at night, and in the morning there's no wind. Same problem. So what I'm trying to say is that when we calculate that energy output, we need to realize that when does it come out? Is it coming in the time of consumption, or do we need to store it so that people use it from night to morning, or even worse, store it from summer to winter, right? So unlike the solar, which is a little bit more predictable, like we know in the solar energy, there's variation between the summer and the winter, and we can, from the graph, you can see you get 20% more in the summer, say, and 20% more in the winter. But the wind, there is not really that nice curve that you can predict. It's pretty random. Okay? So over here, in this example, he said that the analysis believe that the average wind speed, and again, it's a really big deal. When is that average? Is 7.5, which will make the site commercially viable. That is a big statement. Okay, I did one analysis earlier last semester for a site, and the average was great, but we told them this will only work in the summer. You have no wind in the winter. So yes, you will get your kilowatt hour, which turn into money, but use them in the summer because you cannot use them there is nothing in the winter. Okay. All right. So he said if the average is 7.5, what will be at what height will that speed be obtained if the wind is 0.2? Okay. Let me read this slowly so that we can get it. So that table was done at 30-meter elevation. All right. A wind analyst evaluate the data and summarize that if the turbine height is increased, the site may be valuable for commercial wind venue. The analysts believe that an average wind speed of 7.5 will make the site commercially viable. At what height will that wind speed is obtained? Okay. So to put this into a sketch, and I really suggest that we always, even if the problem didn't say, I always think it's really great if you plot your problem as a sketch. It's really clear your mind about what is the solution. So we are trying to figure out what is that height so that what happened, so that the velocity is 7.5 meters per second. And at 30 meters, there is a velocity here because we cannot afford two unknowns, sorry. So that Z we don't know, and that Z1 is 30 meters. So what do I need to do in order to get that height Z2, where the velocity is 7.5 meters? What's missing? What's missing? Help. What's missing in this problem? He said, what height will the velocity be 7.5 meters per second? The average velocity, so that I can install the wind turbine there. If the wind turbine set at 7.5, we will work, we will get money. No, that's already given, alpha 0.2, the wind shear value. Z1 is the height at which this table is being generated. Yes, that's what he's asking about. But there is something else missing so that I can solve this problem. Because I can only afford one unknown, which is Z2. What else is missing? Huh? What else is missing? No, you mean the average velocity at Z1. V1 is missing, right? Yeah, we need to get this V1 because the equation is what? V2 over V1 is Z2 over Z1 to power alpha. Yes, the two velocity are related to the two height by alpha. So if he is after Z2, and I know Z1, and I know it's required that V2 is 7.5, then I have to provide V1. What's V1? The average velocity at that height. I have a table. I don't see the average velocity. How can I find the average velocity? Don't read. How can I find the average velocity? You were given a table of all the velocity at that place. How do you get the table out of it? Sorry, how do you get the average velocity out of it? Yes, yes, yes. The average velocity would be sigma, vi hi over 8760. Yes. I had one student one time, and he was a graduate student. I gave him a table, similar table like this, and the problem was, let's get the average velocity. What did he do wrong? Yes, he basically added this and divided over the number. He added like 1.5 plus 2.5 plus 3.5, and then he divided over 10. No, that's if they are, yeah, if they come, like if someone say I have 10 children and here is their weight, give me the average weight. Yes, add all the weight of the child and divide over 10, sure. Right? But if I have one child that's 50 and 3 children that are 150 and 4 children that's 30, you cannot add the 3 weights. You have to add the raw data, right? Make sense? Yeah, but we will, so we can check on this, but he already told us it's 5.57. So we can use that in the law, right? And don't freak out from the 1 over alpha. What is going on? Why it's 1 over alpha? Why not alpha? Yeah, because it's the z. So u over u is z over z to power alpha, and it doesn't matter which is 1 and which is 2, right? Or the u over u to power 1 over alpha is the z over z. Make sense? Alpha or 1 over alpha. Alpha on the z side or 1 over alpha on the u side. Okay. So he figured out that that height is 133 meters. If he build a tower all the way up to 133, what will happen? The velocity will accelerate or get to the right value he wants. So he can make more money. Good? Very good. So now we know how we can take the data up from one height to the other, right? And at that wind speed or at that height, we just realized that the wind is not going to be constant. There's a table. There's a table that this turbine will run at, right? So the turbine is not going to always be at the optimum velocity, so that you can hit the tip speed ratio of 7, so that you can get the rated power, right? It's not going to happen. So you can see that this is the velocity triangle at the airfoil. This is the plate. The plate is like an airfoil, right? And as V wind change, if I get stronger wind, V relative will be different for the same U. You see that velocity triangle? How V relative plus U plate equal wind. And you also see that why, if the wind come like this, that plate will be pushed up, right? The wind come, he will have to be pushed up. And so why V relative is like that? Because wind speed coming, plate going up, that must be V relative. Because V relative plus U equal V absolute. Okay? So if if that blue direction or this green direction is V relative, and I have an airfoil like this, then this is the lift and this is the drag. The drag is always in the direction of V relative. This is important because a lot of time people think drag is horizontal and lift is vertical. That's in the wind tunnel because our wind tunnel is always horizontal. So the wind is coming like this, the lift always take you up. But if the airplane is moving this way, if you are a fighter jet and you're going up like this, trying to climb up, where is the lift and the drag? That's the lift, and the drag is in the direction of your wind. Okay? Makes sense? So the lift is always normal to V relative, not vertical up. No, it's relative. It's normal to the wind direction. Okay, so that's the lift and that's the drag. So if we, this is really interesting. If we split the lift into this component and this component. And to do this, you need this angle theta or something. So this will be L sine theta, and this will be L cosine theta. What does the L cosine theta do? That vertical component of the left. That's the driving force. That's the one that pushes you up, right? It will help the plate to keep moving. That's what's driving. And what does the L cosine theta does? That's the wind pushing on the plate. That's the axial force. That's the force that the bearing need to take and the tower need to take. That's the price for standing in front of the wind. Okay. Now the drag, we said the drag is the direction of the wind, right? So if I split the drag, I will split the drag into this component and this component, right? And this actually have to be theta because 90-degree thing. So this will be d cosine theta, and this will be d sine theta. So what does the d cosine theta do? This force pushing down, is that helpful or not? So the drag is, as always, annoying, right? So the drag, whether you are a wing or a propeller or a wind turbine, the drag is always bad, right? The only people that benefit from drag are the Viking, right? They like drag because it pushes their ships. But any airfoil, they suffer from the drag. And that's why we want to design the wind turbine plate so that it can really have very high lift, very smooth drag, very smooth drag, right? And those two components, those two axial components, they are just pushing on our bearing, right? Questions? This is the wind. The wind is coming, flowing toward us, right? But this is absolute velocity because the plate is moving up. That is V relative. And V relative is why the wind, that relative velocity is why the drag is like this and why the lift is like this. And that's why the airfoil also is done like this in that angle so that he can adjust to the wind direction. And if you look to actual wind turbine, you will see the plate is twisted from hub to tip because of what? So I said the airfoil need to be ready for V relative. Why will the plate be twisted? I said that in chapter 2. Yes, and why will the relative velocity change from the hub to the tip? Yes, because U is different. So for the same V absolute, U is smaller at the hub and bigger at the tip. So the tip will see the velocity coming like really steep compared to the hub, that the hub will think that the velocity is coming horizontal almost. But the tip will think the velocity is actually He will more see U rather than V, right? So that plate will be twisted. So now the surprising thing about airfoil in wind turbine is that they are not as sleek as airplane airfoil. I mean, if we let's jump a few slides and look at the plate and see how does it look like. And it's not, I don't want you to think that this is just a structure thing. They want it to be strong and sturdy. But also airfoil is designed in such a way that we still have one more lecture. So but look at the plate. It's done in such a way that it's not optimized for one speed. It's basically, rather than being perfect like an airplane that's perfect for a cruising speed, because we know if we are in an airplane, we are flying at Mach 0.85. This is your speed, make the airfoil perfect for that speed. But this guy has to do what? He has to work okay at big range, rather than perfect at 14 meters per second. Any higher or lower, I'm not working. No, you have to work at 14 and 10 and 13, and right? And so you can see that that turbine has a range. I'm going to finish with this. It has a range of velocity at which it's supposed to operate. This is the power output. This is one of the biggest wind turbine. It's 8,000 kilowatts. Okay, that's 8. That's the output. That's the power output from it. This is not input power. This is power output, right? So that's 8 gigawatt, right? Sorry, 8 megawatt, what I'm saying. That would be nice if it's 8 gigawatt. That's 8 megawatt, right? So the power curve is this. Okay, what is this curve mean? The power output, you will get this 8 or like 7.5 megawatt when the wind reach that speed. This speed is the rated speed. If you give me, let's call 14 meters per second. If you give me 14 meters per second, I will give you the rated power. But if you are, I mean, let's make it correct. 16. If you give me 16 meters per second, I will give you rated power. But anything less than this, there is not enough energy in the wind. It's not like my CB is bad. It's just that there's not enough energy in the wind, right? So the input power is something like this. This is the input power, the half rho AV cube. But the output power is we will get whatever you got for us until we get the rated. And then once the velocity increase, the wind is more than the rated power. I already delivered rated power. I'm gonna cap. I'm not gonna go up. Why? My generator is rated. The wires, the bearing, the everything else in the base of the tower, I cannot deliver more electricity than this. So what do you do from this point forward? I will have to make my turbine suck on purpose. Okay? So what do you mean you make the turbine suck? So that's the second curve. That's the CP. So you can see that they hit the maximum CP of 0.49 for 3-plate turbine. Not 0.59. No one get 0.59. But they get 0.49 in that range. And after that, when the wind speed start to pull up, they drop their CP. How do they drop their CP so that they maintain the power output? What's in their hand to drop their CP? How can you make your airplane suck? That velocity triangle should help you. How can you make it suck? You make the angle not really that great, right? Why would you optimize with the wind? No, let's suck. Let's change the angle, right? With a certain mechanism that basically the pitch angle deteriorate so that we will actually not get the maximum performance. So that the power is higher and higher, but we are not going to get more than that power. Let's basically lose the lift in the street. We don't want to get it. Thank you so much. I will see you next week.